Right, in this video, I'm going to begin round two of talking about correlations. Correlations are a topic that deceptively has more depth to it than you might expect. So, to start off the first video for this second part of your correlational material, I'm going to cover how you can plug correlational analysis with your Pearson's R into the hypothesis testing framework. So, basically, when you run a correlational analysis, you want to evaluate your obtained R value for statistical significance. That's why when you run a correlation in, say, SPSS, there's a p-value attached. So first things first is going to be to figure out how do you put correlation into the hypothesis testing framework, understanding how to evaluate for statistical significance, and slightly more in depth, what specifically does the p-value attached to your Pearson's R mean more specifically. So this is going to be our first foray into plugging a specific analysis into the hypothesis testing framework, but the basic paradigm is going to be the same for all of the tests we'll be learning from here on out. We obtain a statistical outcome, we evaluate it for significance. So I'm going to do a slight callback to the hypothesis testing lecture and revisit a p-value. If you remember, understanding a p-value was one of the main points that I hoped you would take out of the hypothesis testing lecture. So a p-value, so called because it's a probability value. Specifically, a p-value is meant to be the quantification of your type 1 error rate, otherwise notated as alpha. So the basic approach will be to ask ourselves, what's the probability of being mistaken should we claim that we have found a significant effect? Again, this is your type 1 error rate or your false positive error rate. So a p-value, no matter where you see it, is essentially a quantification of your type 1 error rate. That's why we tend to not like higher p-values, and we want, all things being equal, smaller p-values, because a higher p-value indicates a higher likelihood of making a false positive, which is, again, the sort of worst sort of mistake you can make, because it is to affirmatively claim you found something and to be mistaken. So what we do is we compute whatever statistical analysis is appropriate, and then we want to evaluate the strength of that outcome. We want statistical outcomes, numerical outcomes that are strong enough, impressive enough, that they yield smaller and smaller p-values. This indicates that should we declare on the strength of our evidence that we have a real effect and declare our results significant, a smaller p-value is going to equate to a smaller probability that we've made the false, erroneous choice. So, again, all things being equal, smaller p-values are more ideal, as they indicate a smaller chance that we might be making a mistake should we claim significance. There is typically an inverse relationship, though, between obtained statistical outcomes and their associated p-values. In the context of correlation, larger correlational coefficients are associated with smaller p-values. The idea is that stronger correlations between truly unrelated variables are going to happen theoretically very, very few times over the course of the underlying probability distribution. Having sort of small correlations between truly unrelated variables, just a greater chance that that is a reasonable fluky thing that you might encounter. But if you were to find an absolutely extremely strong correlation between truly unrelated values, well, that's just a rarer outcome that you're going to see a much smaller percentage of the time. So for that reason, a larger correlation is going to have an associated smaller chance of yielding a false positive result. So that's where this inverse comes into play. All things being equal, the larger your correlational coefficient, the smaller the p-value it's going to have associated with it. So we can apply hypothesis testing through all its steps to a correlational analysis. You want to state the null and the alternative hypothesis for your reference. Here's where you're going to decide if you're going to use a directional or a non-directional approach. If you're using a non-directional approach for creating a hypothesis for correlation, essentially that's when you predict that there's going to be a correlation, but you won't state whether it's positive or negative. You're willing to accept a correlation in either direction. So if you think your variables will be related, but you have reason to think it might be in either direction, go the non-directional route and set yourself up for a two-tailed test. A one-tailed test, on the other hand, in the context of correlation, is when you either predict for your alternative hypothesis that your Pearson's R will be above zero or below zero. You can predict a correlation in either direction. Just whatever direction you choose, know that your null hypothesis needs to be the logical counterpoint to that alternative. You set your decision rule. Just go ahead and use p equals 0.05. This really, again, is the sort of industry standard in the field of psychology. We're willing to accept p equals 0.05 as the sort of minimal bar for significance that we would accept. So unless you have reason to think you want to set a stricter decision rule, just go ahead and use the status quo of p equals 0.05. Just know that you're going to have to stick with that when you ultimately analyze your data. So if you end up with a p of 0.06, you're going to have to accept that disappointing non-significant result. From there, this is when you actually do your statistical analysis, which we spent a lot of time talking about in the last video, right? Actually calculating your Pearson's R is where it feels like most of the work actually happens. And this will be true for all our subsequent statistical tests. It's all about learning which test statistic we use and how to do it. From there, we need to figure out the statistical value for a Pearson's R needed to achieve at least a p equals 0.05. We need to basically find an R value that represents that critical probability cutoff. If our obtained statistic exceeds that critical cutoff, that's when we would declare our correlation is statistically significant. Basically, that's a correlation that's larger than likely to happen 5% of the time. So I'm just going to refer back to the practice problem from the last slideshow where I was looking to calculate the correlation between this hypothetical data associating nostalgia with happiness. So in the case of this particular hypothetical, if I had set up the hypotheses to be a non-directional test, my null and alternative hypothesis would look like this, right? If I was predicting that nostalgia will affect happiness or be associated with happiness, because I might think that possibly people who are more nostalgic are happier, but I also think it would be interesting if people who are nostalgic were less happy, maybe because they're thinking too much about things that are not true about their lives anymore. I might want to do this two-tailed approach. That opens the door to either find a positive or negative relationship between those variables. Then your null is again just going to be the logical counterpoint. So if you're making a non-directional correlational hypothesis and you're saying that one variable is associated with the other, the null is just going to be that there's no relationship between the two variables. Again, if you're going directional or one-tailed, things are going to look a little bit different. We're going to operate primarily under the assumption that this example was using a non-directional or two-tailed approach, but I will show you the implication of two-tailed versus one-tailed predictions for significance testing. So the first step to be able to find this critical R value that you'll be comparing your obtained R value to, one is that you'll need to determine the degrees of freedom associated with your sample. So we've seen degrees of freedom before, for example, when we learned how to compute the standard deviation. The denominator of that formula was n minus 1. The 1 was just standing in place for the one variable currently under consideration. Degrees of freedom in the context of correlation is going to be n, or sample size, minus 2. The 2 representing the two variables currently under consideration. So the degrees of freedom for this example, with 10 participants minus 2, you have 8 degrees of freedom. The reason we need to have this information in order to find our critical R value is that the sample size you have, more specifically degrees of freedom, but degrees of freedom are derived from your sample size, is that the sample size shapes the underlying probability distribution that determines our critical probability cutoffs. Basically, if you were to have fewer participants, the likelihood of getting extremely strong fluky results is just more within the realm of possibility. If you're only sampling a few people, there's a greater chance of getting kind of extreme fluky results. But as you get more and more participants, you start to see that probability distribution be a little bit more normal. If you have a sufficient sample size, basically the idea is those very, very extreme results are not going to be the result of chance a large percentage of the time. So all of this is to say, we need to know our degrees of freedom and the decision rule we're going to apply, and then from there find our critical, Pearson's R value. You don't need to do any calculations for this. Finding your critical statistical values for all of the tests we'll be doing is just a matter of being able to use and interpret a critical value table. So there's going to be a different critical value table for our Pearson's R, for our t-test, for our ANOVA, and for our chi-square. They all kind of work the same way. Basically, you're going to need to use your degrees of freedom, which are listed in this column over here to the left, to orient yourself to whatever row contains your particular degrees of freedom. So we have 8 degrees of freedom, so we're necessarily going to be finding our critical R value somewhere within that row. Then from there, we need to look upwards to those level of significance values. Those are our critical probability values. And we need to find the column that represents our decision rule. So you'll notice that there's a row for level of significance one-tailed and a level of significance for two-tailed. And you'll notice that they're stacked one on top of the other. This is, if you remember, when we learned about regions of rejection from the hypothesis testing lecture, just a virtue of the fact that when you go from a two-tailed test to a one-tailed test, you're essentially doubling the region of rejection and placing it all together on one side. That has the effect of making it technically easier to achieve significance with a one-tailed test. So if you notice, you've got one row containing critical values corresponding to p equals 0.05 one-tailed, meaning that if you reach any of the values in this column, you would achieve significance. The associated two-tailed p-values for this same column, though, is 0.1, meaning that if you were to use a two-tailed test, any of the values here in this column would not achieve significance. So if mostly at this point you just want to know how to use the table, basically just figure out whether or not you're using a one-tailed test, and if so, find the p equals 0.05 column here, which is this one all the way to the left. Or if you're using a two-tailed test, make sure that you're looking in the column here representing p equals 0.05 critical probability values for a two-tailed test. Okay, so make sure that you set in advance whether your prediction is directional or not, because that will impact how you use this table and your likelihood of finding a significant result. So if you're just going to use p equals 0.05, which unless otherwise directed, you should, you would find the significance value of p equals 0.05 in either the one-tailed or two-tailed row. Then from there, you find the intersection of that significance level column with your degrees of freedom row. That there will have a single value there at the intersection between the significance column and the degrees of freedom row. The value that you find is your quote-unquote critical R value, which I always notate as R sub crit. Then, as I mentioned, you compare your obtained statistical analysis to your critical cutoff. If your obtained R value exceeds R critical, then you have a significant result. So, to use our example, like I said, we have 8 degrees of freedom. We're going to use a two-tailed approach, so use that column with p equals 0.05 for two-tailed test. And as you can see, the intersection of that column of row, therein lives a single value representing R critical for this particular example. So R critical is 0.632. The question now is whether or not our obtained statistic exceeds it. If you recall, the R value from this example was 0.78. R obtained exceeds R critical, and in this case, that means that this result is significant. Okay, this is an important point because this is going to come up for all our subsequent analyses. When your obtained statistical outcome exceeds the critical value, that means your correlation is significant. And this is going to be true about all the further analyses we do this semester. One point I'd like to make here, because this is often a source of confusion, is that when interpreting your Pearson's R for significance, you use the absolute value of the R value. In this case, it didn't matter because this was a positive correlation anyways. But do recall that the magnitude or strength of the correlation is about its distance from zero. So when you're evaluating your Pearson's R for significance, if you have a negative Pearson's R, make sure to take the absolute value of that R when you go to interpret significance. Don't get rid of the negative value when you write up your correlation. Just when you interpret it for significance, make sure that when you evaluate it against the critical R, you take that absolute value first. Because if this correlation had been negative, let's say it was the correlation between nostalgia and anxiety, and that correlation was negative 0.78, that still would have been significant because it is about the distance from zero of your R value when you're interpreting the magnitude. So key questions when you're going into this process of determining your correlation for significance: determine whether or not you made a directional or non-directional hypothesis, because that will lead you to either a one-tailed or a two-tailed test. So language like variable X affects variable Y, that's non-directional language. And again, this is important to do in advance because it is technically somewhat easier to achieve significance if you use a two-tailed test. So if you had gone in with a two-tailed prediction and you only achieved a p-value of, let's say, 0.06, you might say to yourself, well, if I flip it to one-tailed, wouldn't that achieve significance? Yes, that is exactly what would happen, but it's unethical and sketchy to do that. So since you technically can have smaller correlations to achieve significance one-tailed, make sure that you're only using one-tailed if you had a good, solid justification in advance to do so, because a smaller correlation will technically be able to help you achieve significance using the one-tailed test. SPSS automatically uses two-tailed, and you can too. If you're ever concerned about making the right choice, one-tailed or two-tailed, you would never be docked credit for erring on the side of using two-tailed. So to demonstrate this difference between two-tailed and one-tailed and what it means for significance, here's what I mean. If instead, in the same hypothetical, I had used a directional prediction, I said, I think nostalgia is positively associated with happiness, I would have been living here in this column representing critical values for p equals 0.05 one-tailed. Notice that that Pearson's R is a smaller critical cutoff than the one with the two-tailed test. This is technically an easier bar to achieve. It's easier to achieve significance with a one-tailed test. Hopefully, it's not the difference maker, one-tailed versus two-tailed. You would hope that it's significant either way, but since it can technically have an effect on your declaration of significance, make sure that if you want to use one-tailed, you make that prediction in advance. Okay, so then to review just a couple more points on this subject. Again, our Pearson's R was 0.783, and it was indeed significant, but I do want to briefly mention that this specific p-value associated with that R means something a little bit more specific than just it being less than p equals 0.05. Yes, to achieve significance, all you need is to make it past that p equals 0.05 cutoff, but this specific p-value of p equals 0.007, it actually means something in mathematical terms, and I want to make sure to explain that to you. This R value, it exceeded p equals 0.05, but it even exceeded p equals 0.01. Right? That p-value is even less than 0.01. That means that it's not just significant, it's what we would call highly significant. Another thing I like about this table, even though you only need these 0.05 columns to determine significance, the fact that there's a variety of critical values up there at the top indicates that you can actually be a little bit more specific about which significance value you have achieved. So for example, if you look further over in that degrees of freedom 8 row, right, you know that you made it past p equals 0.05 because our r of 0.78 made it past this 0.632. But we also know that it made it past p equals 0.02 because 0.78 made it past 0.715. And it also made it past p equals 0.01, which is what SPSS told us, right? An R value of 0.78 even makes it past this p equals 0.01 bar, which you know, because our obtained R exceeds that R critical for p equals 0.01. Now we don't make it past p equals 0.001 because that critical R is 0.872, as you can see here. So what that leaves us is a statistically significant correlation at the p equals 0.01 level, but no more than that. Now what the specific p-value means is that even with a two-tailed test, a Pearson's R of this magnitude with this degrees of freedom is only going to occur among non-related variables less than 1% of the time. We're very far into the region of rejection. This strong of a correlation with this underlying sample size can theoretically occur with unrelated variables, but just very, very rarely. This is why we would declare this particular correlation highly significant. And even more specifically, the p-value associated with your results, it does mean something in probability terms. So we have made it past p equals 0.01, but a p of 0.007 specifically means that a correlation that strong will, in probability terms, only occur 0.7% of the time. So hypothesis testing, it evaluates for significance and it gives you a specific probability value associated with your results. And now just to wrap up with this section on hypothesis testing for correlations, a few more points, including an example from some real research, again on this topic of nostalgia. This particular research was interested in the extent to which nostalgia was associated with feelings of authenticity, sort of the extent to which you feel like you're a genuine person who does things for yourself and not for other people. So this authenticity variable was measured a couple different ways. One was by asking people a series of questions about how subjectively authentic they thought they were, but it also attacked this construct with what we call extrinsic self-focus. So this is going to be the extent to which people report that they do things because of external demands and expectations as opposed to what you want to do. These are really just two distinct ways of measuring the same construct, but the researchers wanted to make sure they were attacking this construct from multiple angles. So then, this is the graphic from their first correlational study from their publication. Now, I refer to this graphic a lot because I think that this is the ideal way to depict data like what you're going to get from your project. So whenever students ask for advice of how to visualize their data in the final paper, I point to this graphic and recommend creating something like this. So this is a table that not only has columns for the descriptives for all three of the variables in question, it contains over here a correlation matrix, but it's all cleaned up. I've mentioned when talking about the lab quiz that this diagonal here represents unimportant information because this box here, where it's nostalgia over 1, this box would represent the correlation between nostalgia and nostalgia, which is obviously 1-to-1, but we really don't care about correlating a variable to itself. It tells us nothing. So this diagonal has just been blanked out with a series of M dashes. The lower half of the matrix has been left blank since that would be inherently redundant information. And the primary correlations are only depicted once. So this here, this 0.26 represents the correlation between nostalgia and authenticity. This here in row 1 and column 3 represents the correlation between nostalgia and extrinsic self-focus, and those are the primary correlations the researchers were interested in. One point I like to make here is that you might be thinking to yourself that this correlation here, that negative 0.68, you might be thinking that's the most important correlation depicted here because it's the strongest. This is a point where it's important to keep in mind that the most impressive or valuable correlations from this study were about linking nostalgia to other variables. This correlation here is the correlation between authenticity and extrinsic self-focus. Like I said, those were just two different approaches to essentially tapping into the same construct. You would necessarily predict those variables to be related because theoretically they should be. They're basically tapping into a similar sort of idea. So despite the fact that that's the strongest correlation, we actually care about it the least. So you always need to make sure you're going beyond just looking at the numbers to thinking about what they mean and what the story is that they tell. Again, these two correlations represent nostalgia being associated with something else that is distinct that you might not have expected. So that's why these correlations, despite being smaller, are actually more impressive. It's because they're more interesting. But that basically would be a way that you would visualize a correlational matrix in good, clean APA format without redundant or unnecessary information. I'm going to bring back up this concept of your coefficient of determination because, as I mentioned, this is one way that you can interpret your correlational research. If you were to take the correlation from that publication on the previous slide that depicted the correlation between nostalgia and authenticity and square it, you would get a 6.78% of the variance in authenticity is accounted for by differences in nostalgia, meaning that the vast majority of variance in that authenticity variable is due to other factors. This is okay. One, it was still significant, so that means it's at least somewhat of a meaningful component of authenticity. But also, again, it's important to keep in mind what the variables are you're studying. Authenticity, the extent to which you feel like you're a genuine person, is obviously a complex and multifaceted construct. And the extent to which you feel authentic is likely going to be comprised of many different aspects of your personality and things going on in your life. So nostalgia is sort of an unexpected chunk of the variance in the construct of authenticity. So despite the fact that it's not overwhelmingly helping us understand the amount of authentic that somebody feels they are, it's still a meaningful component. But it's important to keep in mind that if we're dealing with complex, multifaceted constructs, it's okay that it's a relatively small correlation. It's still significant, and it still has a surprisingly large chunk given how distinct nostalgia is from authenticity. So I'm going to take a pause here before starting the second video of this part 2 of the correlations lecture on complex correlational design.